Okay, today we're going to look at Newton's gravitational law. It's a little bit different than his first three laws, but it kind of uses ideas off the third law to figure out how gravity works. So far we've already looked at a basic formula for force of gravity. We did the force of gravity equals mass times acceleration of gravity. So for example, if we have a 100 kilogram mass, we times that by 9.81 for the acceleration of gravity on Earth, and that gives us a force of gravity of 981 newtons. The key thing to remember with this is that only works for the Earth, and it only works for objects that are on the surface of the Earth. So objects on the surface of the Earth, our gravity is 9.81 meters per second squared. But as soon as we go to different planets or moons or anything else, that number would not be valid anymore. And it also isn't valid if we were not on the surface of the Earth. So if we're up in space or something on a space shuttle, a certain distance from the Earth, then that gravity would be different as well. So the key thing to remember is our basic formula, Fg equals mg, that only applies to gravity on the surface of the Earth. So what Newton wanted to do is he wanted to figure out what gravity is between any two objects. And the formula he came up with is actually was used first, and that once you simplify it for Earth, then we use the mass times 9.81. So we'll get to that a little bit later on how he came up with the 9.81 number. But so we're going to backtrack a little bit and kind of figure out how any two objects, whether they're planets or people or rocks or whatever, have gravity between them. So Newton's theory was we are attracted to the Earth because there's gravity. The Earth is pulling us towards it, but we're also pulling the Earth the other direction. So he said if you have any two objects, there's always going to be a force of gravity between them, no matter how big or small they are. So what that means then is, how does that force of gravity compare? So what Newton did a bunch of calculations and stuff, and he figured out that the force of gravity is going to be proportional. So this little fish symbol is just a combination. It just means sort of it's not equal to, but it changes according to mass 1 times mass 2. So his logic was that if we increase the mass of one object, then obviously the gravity is going to be increased as well. So he's using sort of his third law idea, saying that every action is an equal and opposite reaction. So if mass 1 is pulling mass 2 towards it, mass 2 is also pulling mass 1 towards it in an equal and opposite direction. So therefore, the forces of those two things getting pulled together is what Newton called the force of gravity. Okay, so if these two things are proportional to each other, so that means if we increase mass 1, the net force is going to go up. If we increase mass 2, force of gravity is going to go up. If we decrease one of the masses, obviously, then it would decrease as well. So you're going to get questions where it'll say things like, if mass 1 is doubled, what's going to happen to the force of gravity? So let's suppose, for whatever particular question, we have a force of gravity of 100 newtons, and the question is saying what's going to happen if we double mass 1? So if we double mass 1, because they're proportional, basically we just go 100 times 2, so that means our new force of gravity would be now 200 newtons. Okay, so what would happen if, let's suppose we're 100 newtons again, but let's suppose now we double mass 1 and we triple mass 2. So we have 2 times mass 1, 3 times mass 2. So together those are going to be 6 times larger. So we'd have 100 times 6. So that means our new force then would be 600 newtons. So you get the idea. Whatever the masses change, you just change your answer by the same. So what would happen if we double mass 1, but we cut mass 2 in half? So in this case, 2 times a half is, we're back to 1. So if we double 1 and cut the other one in half, nothing's going to change. So we would just get the exact same original net force. Okay, what Newton also said then is, how else can we change the force of gravity between two objects? And he said if we change the distance between the two. So obviously if you're on the Earth, there's a stronger force of gravity than if you were up in space. Or if you're a distance from the moon, there's a stronger gravity pull towards the Earth as there would be if you were out at a different planet like Venus or something like that. So the closer the objects, the more gravity you have. The further objects, the less gravity they have. So what Newton does, because objects can be different shape and sizes, he measured the distance between them as measured from center to center. So if we measure from the center of one object to the center of the other object, we'll call that our distance r. Okay, so what he said then in terms of the gravity is our distance, our force of gravity is actually proportional to the distance squared, 1 over the distance squared. So what that means is as we get bigger, as our distance gets larger and larger, our force of gravity gets less and less, but it's not just timesing it by that distance or dividing by the distance, we actually divide it by the distance squared. So he did lots of calculations to figure this one out, but it actually indeed works out true. So we can do the same kind of questions again. So let's suppose we have 100 newtons of gravity between two objects. What's going to happen if we double the distance this time? So in the formula, if we put 2r in place instead of just r, that's going to double the distance, but because it's squared, it's actually going to be the same thing as a quarter. So we'd go 100 times a quarter, which in this case would be 25. So if we double the distance, it makes it 4 times smaller. So what would happen if we half the distance? So if we took the 100 newtons and we did 0.5 of the distance, so we'd have 0.5 of r squared. So when you do 0.5 squared, you actually get 0.25. So that would give you 1 divided by 0.25, which is the same thing as timesing by 4. So if we go 100 newtons times or divided by 0.25, we'd actually get 400 newtons. So if we double the distance, we get 4 times smaller. And if we half the distance, we actually get 4 times bigger, just because of that whole squaring idea. So let's do one more. We kind of combine the two ideas together. So if we have 100 newtons, what's going to happen if we kind of combine these two formulas? So we got to have mass 1 times mass 2, and we divide by r squared. So in this case, let's suppose we double mass 1, triple mass 2, and we double our distance. So you do the same thing, but you just do all these steps together. So that would be 2 times 3 on top, and 2 squared is 4 on the bottom. So we'd go 100 times 6 divided by 4 works out to 150, I think. Let me just double check that. So that'd be 200, 600 divided by 4 is 150, yeah. Okay, so you can do these kind of questions. They're all kind of the same. The only thing that changes is whether you're doubling, tripling, halving, whatever. So just put the numbers into that sort of formula, times your answer by whatever you get, and you're done. So if we put these two ideas together, so Newton said we know that it's proportional to mass 1 times mass 2 divided by r squared. So he said it wasn't just equal to those, there was some sort of constant factor involved. So he called it big G, which basically stands for some sort of gravitational constant. So that means there's some sort of number times mass 1 times mass 2 divided by r squared that would actually give us the force of gravity between any two objects. And he never could find out. The problem was if he only had Earth to work with. So if we had a person standing on Earth, right? So we have our mass 1, we have mass 2. We knew the distance. Back in his day, he actually knew the distance. He knew the radius of the Earth. That's why he called it r, because it was dealing with the Earth, so radius of the Earth. But we didn't know the mass of the Earth. So without the mass of the Earth, he couldn't figure out what the force of gravity is. So he left his formula just like that, but he could never actually use it to figure out what the number G was. So it took about 100 years later, Henry Cavendish came up with an idea where he could actually figure out G. So what he did was he used a torsion balance, which is basically just a balanced metal rod. So he had these lead masses on each side. So they were quite heavy, and he had them a certain distance apart just so that they'd balance out. And then he took other lead masses and he put them near it. So he kind of put one sort of in front of this one, and then he took another one and put it behind this one. So what happened is, once they were close enough, so you could measure the distance that they were close enough, then what happened is there was a force of gravity attracting the torsion balance to those other metal spheres. So what he did was he could measure the distance, he knew the masses of the two objects, all he had to do was figure out what the force was, and by that twisting motion he could actually calculate the torsion of that twist, which is equal to the force of gravity in this case. So after a whole bunch of experiments and a whole bunch of calculations, his torsion balance allowed him to calculate what G is. And to this day we still use his number. It's 6.67 times 10 to the negative 11. So that is a gravitational constant that we use every time when we calculate the force of gravity. Once he could figure out G, he then actually plugged it in the formula and he could calculate the mass of the Earth as well. So the mass of the Earth is another number that we use quite often, and it's on your formula sheet. So the mass of the Earth is 5.97 times 10 to the 24 kilograms. And we also use, for the radius of the Earth, we use 6.27 times 10 to the 6 meters. So those are numbers we often use when we're dealing with the Earth. But in the Cavendish experiment, he knew the radius of the Earth, or close to it, so he calculated G, and then once he had G, he could plug it in the formula to calculate the mass of the Earth. So he actually titled his findings Weighing the Earth, is what he called it, to be able to figure out how big the Earth's mass was. Okay, so what we're going to do is we're going to use the new force of gravity formula to calculate the force of gravity between any two objects. So it doesn't matter how big or small they are, we can always calculate the force of gravity between two objects. So let's suppose we calculate the force of gravity between two people. So let's suppose one person weighs 75 kilograms, and let's suppose the other person weighs 60 kilograms. Let's suppose they're standing half a meter apart. Okay, so two people standing there will actually have gravity pulling them towards each other, so let's figure out how much that would actually be. So in your formula, type in 6.67 to the negative 11 times 75 times 60 divided by 0.5 squared. So it's a little bit more complicated to type these in just because the exponents and things like that change a little bit, but it works out exactly the same. So if we go 6.67 times 10 to the negative 11 on your calculator, use the EE button. So all you have to do is type in 6.67 EE negative 11. You don't need to put the times 10 in. And then times that by 75, times it by 60. It equals, divided by 0.5 squared, gives us an answer of 1.2 times 10 to the negative 6 newtons. Okay, so any two people, 75 kilograms, 60 kilograms, standing half a meter apart, they're going to have 1.2 times 10 to the negative 6 newtons. So that's a pretty small number, right? 1 newton is just a light touch, so 1.2 to the negative 6 is pretty much zero. That's like a millionth of a newton, so not enough to do anything. That's why when you're standing next to somebody, all of a sudden you'll get pulled together. Like the gravity isn't big enough to make that happen. So you can see the only way we can actually get gravity big enough is we need masses that are really big to be able to counteract that times 10 to the negative 11 number for the G. So if we made masses like the size of the Earth, then there would actually be enough gravity that you could notice something. But Newton's formula does work for any objects, any size, any distance. Other questions you're going to get, maybe we'll ask for things like, if they give you the force of gravity, what is the distance r, or what is one of the masses? So you can rearrange this equation and solve it for any other unknown as well. And we'll stop there.